nice to be here again. So yeah, mainly memory it will be today. We didn't get to the energy part yet. So for those who don't know kind of like what we're doing, our kind of like embedded software stack, many of you have seen this slide already, but kind of like a quick recap, traditional architecture of the Erlang VM running on, let's say, Linux. And Linux runs on hardware, and you need to go through Linux to get to the hardware. And we kind of like baked everything together with a thing called RTEMS, which is kind of like a library, which is an operating system-ish thing. You would call it a unikernel nowadays, and boot the whole thing directly on hardware. So if you go out into a NIF, you're talking to the hardware registers. So there's no kernel in between, which gives you very low latency. And because of RTEMS, it's hard real-time. It turns Erlang soft real-time into something much harder already without you having to do anything, and you can also have hard real-time. So that was the quick thing. We made kind of like a series of boards to get people started quickly. So that's our second board. The first one we were not so happy with, so we did a second one pretty soon-ish. So this one is kind of like has plenty of space. It would also run Linux because we wanted to support nerfs with it, and it is a officially supported board for nerfs. Let me start my timer here. So we have 256 megabytes of RAM. We have virtual memory. It's an iMix 6, which is still power efficient, but well, you can go further. So that was what we wanted to build next. Basically, we wanted to kind of like build something in the three-dimensional space, vaguely, where you have like power and speed upwards and size and cost. We wanted to have something that's closer to the origin, as close as possible to the origin as we can encroach. So the Raspberry Pi is not on this slide. It's somewhere up here because it uses much power. It's a little server. It's not like very power efficient. There's also smaller ones that are more power efficient, but meaning the normal ones. And because the funding was coming from a project, a research project, where the coordinator was doing energy harvesting devices, like from temperature gradient. So you put it on a hot surface, and then you get enough current to run something very tiny. So get very little single-digit milliwatt out of that. We kind of like tried to get the power down, not so much the cost and the size. So that's why the dot is where it is. We have 4 PMODs on it. So this little black connector, so that we can plug in like modules, and it has only 4. So it's actually, I have it here. It actually exists as hardware. Basically one of them is meant for communication, so we don't have built-in communication, but you plug in a PMOD for that. We have ultra-wideband and Ethernet, but yeah, we will get to that. So that's the planned hardware specs. Is like an STM32 U5, which is the very low power one. So that's very low power. It allows very high power savings during running, and it sleeps very deeply, so it's very made for this energy harvesting thing. And also it supports like state-of-the-art Octo SPI RAMs. So SPI is like a serial interface, and Octo SPI is like you replace the one serial line basically with like 8 synchronous ones, like so you have a byte every clock basically, and you can get very power efficient RAMs for that. And yeah, we had all that made, and the PCB was made, and then an errata dropped, and ST told us, no, it doesn't work, and we need to pick 16 megabytes RAMs because that was the only one that were compatible at the moment. Well, this is fine, isn't it? We'll see. Because what we also wanted, we want to run the vanilla Erlang runtime. There's also nano BSD, to give it a shout out, which kind of like try to approach what we are doing from the other direction. So they're kind of like building it bottom up, trying to build their own VM, keeping it tiny, and they can be much more tiny than we are. But for what we want to do is kind of like with distributed computing, we would like to have everywhere the same beam files, and not like have to pay attention. It's like, oh, these beam files can't go over there because they contain whatever floating point or whatever it doesn't support. So we kind of like want to go top down. So we want to shrink Erlang OTP and the Erlang runtime, the vanilla one, and we hope that it's also easier to keep up with that. So that's a larger picture of the board. You can see the it's unfortunately it's not so good photograph. We need to make a better one. You can see the 4 black things that are for the PMODs, for these little modules that you can plug in with sensors and actuators. There's 2 USB here. One is a micro USB that's kind of like for the console, and you can power it over that. And then there's a USB-C, which is actually connected to the CPU, where you can either do USB host or USB client. So you can actually turn the thing into a USB device, for example, on Ethernet, and plug it into a computer, and then you have Erlang distribution already running. Well, eventually. What we also have, like this green thing is, that's for the energy harvester. So we have 3 pins. 1 pin to measure the power that it actually has currently, because it charges a large capacitor actually. And whenever you have enough charge, then you can actually decide to run. A real-time clock, SD card. That's the RAM here, CPU. What else do we have? Like a bunch of jumpers, a JTAG interface. Yeah, I think that's about it. A bunch of LEDs, the usual suspects. So yeah, I'm not explaining all that. So we also put a lot of logic in there, because most of the stuff that's run from energy harvesting is just like really tiny C code running in a flash. So basically, when there's enough power, you switch it on, and immediately does its measurement and does nothing else. Basically, it can run immediately out of flash. But if you have an Erlang VM, we need to boot kind of. We need to load stuff, and we need to do stuff. And so because of that, we kind of like need to then, once we solve the memory challenge, that got a little bit tighter than expected, then we also need to kind of like solve the challenge, how do we actually boot? So we actually have a way to watch to control the energy. Basically, when we're in an unbooted state, we can say we need more charge now, so we can get through the boot. And then while we are running already, then we can actually configure it differently, and we need less charge, and then kind of like say, hey, wake up when we have enough charge like that, and you do the measurement, you send it off over the wire or over the air, usually over the air. And then you sleep again, because that's how you are very power efficient. You run only for a short time, and then you sleep again. So not much more details than that. So we did kind of like, we got the hardware too late last year. So the research project was running the whole year. We only got it in kind of like early December or something. So we did some work on it on December to kind of like basically get it running. And then we were busy with other stuff, with kind of like businessy stuff, which was kind of more important. And now before this conference, but we have been talking about the thing for the whole month. Before the conference, basically we said like, oh, there's 1 week more to go. We need to crunch now. So we did a little crunch, and I wanted to give you a chance to the 4 people who crunched the most, basically, to give them a little kind of like describe GRiSP Nano in 1 sentence, like most of them chose 1 word, by the way. So yeah, I think you can read the names. It's Gwenda, Luca, Sebastian, and Mate.
Small.
Tight. Challenging.
Tiny Erlang goes brr. Tiny Erlang will go brr.
So that was on Friday, by the way. So already the hint, it will go brr. It's not going brr quite yet, so it's work in progress. So let's look at what we have. Like, this is kind of like the console. I mean, you don't need to read all that. I pick out the important things. So basically, we put a lot of like debug stuff in there. We look at the allocators, because the 16 megabyte is a big challenge. Actually, it's not true. We have 16 megabyte RAM and 3 megabyte of internal RAM. So the CPU has its own RAM, but it's disjoint. So you don't have one memory map. So you have like a bunch of bytes here and a bunch of bytes there. So you need to deal with that, which is not always the most easy way. And there's also 4 megabytes of flash, which currently only has the bootloader, which doesn't need all the 4 megabytes. So if you can get the image small enough, you could actually also stick it in flash, maybe. But so that's where we have basically, after loading beam.bin, basically, the actual image with RTEMS and whatever. So we booted the thing into the 16 megabytes of RAM, of the contiguous RAM. We have 7.4 megabytes free. Ooh, that's not much. And we can only load 7 modules. Oops. So that was kind of like the state end of last week. So what we first did is remove crypto, 0.5 megabyte. And we kind of like aggressively optimized the binary, kind of like omit frame pointer and all kinds of things, like kind of like size optimizations of code, basically, with compiler flags. And that looked like that. Oh, 8.5 megabyte free. And beam.bin is got down to 4.7 megabytes now. And we can load 45 modules more. There's many more, by the way. So, no worries, we'll put crypto back, yeah. But this was just like, yeah, we need a bit of space here. We put it out. We will put crypto back because I think we need crypto. Everybody needs crypto. So we added more instrumentation, basically, and created a bunch of data. And basically on the bottom, you see the modules in the order it's loaded. So ERTS code purger, init, that's init. You might have seen init, an error message from init when something doesn't work. And then it goes the prim things. So that's there's a bunch of like preloaded things. And then there's kind of like an interesting thing, persistent term, kind of like uses a lot of memory. And we don't know quite why. We didn't have time to look into it. It might be also that kind of like it's just like we cross the border, that we need another big tile of memory or whatever. We are a little bit confused about that, and then it goes on and on and on. It gets less and less. So you might not be able to read it. The top thing is the total free memory, and the yellow thing, the bottom one, is basically the largest free block, basically, which shows us kind of like fragmentation problems that we might get. So, well, let's strip the beam files, because actually, when they're loaded, they're mapped, they're basically loaded completely into memory, and then only the section that actually matter get loaded where they actually run. So that saves a little bit, but same amount of memory free. We only saved 16 kilobytes, so that was not really worth it. But yeah, we loaded 2 modules more. We're getting there, slowly. Then we did some pretty big RTEMS tweaks, kind of like, because we have a huge thing called libBSD, which is basically the FreeBSD networking stack, which has everything, and also has a USB stack. And at first we wanted to kick it out altogether because and replace it by a smaller TCP stack, but we also use the SD card driver from libBSD. So if we kick it out altogether, we don't have an SD card driver, and we want to boot from the SD card. So yeah, that didn't work, at least not in short notice. We are now slowly starting to use the CPU internal RAM, not in a very kind of like thorough version. We kind of like moved the block storage, like the initialized storage, like the stacks and the block storage, we moved it into the internal RAM because that was easy to be done with the linker. If it was up to me, I would have liked to load basically into the internal RAM, and then when it overflows, load somewhere else. But we got a very tiny bootloader there that only can load one contiguous set of memory. It would actually not be hard to kind of like load ELF files and do this mapping, and I will replace it with a bootloader I wrote because I did that in the past a few times. And then we can actually fill up the memory and also put the emulator into the internal RAM because it's much faster. So then we tried also running garbage collection also after speaking to the OTP team. So thanks to all the good hints and tips from the OTP team at this point. Running garbage collection after each module, because we might kind of like hold on to binaries. You know, the garbage collection is not triggered. You have old binaries dangling off your dead data basically. And so in order to purge them, we run a garbage collection. So that was the largest thing. So you see it's much larger. We have much more free memory, and we can load 25 modules more. Well, getting there, 25 modules by 25 modules. Then we actually tried not running the garbage collector to see how its impact is. And that was surprising. Because if you don't run the garbage collector, we can load 2 modules more. And we don't know why, actually. That's a thing that we need to find out. Yeah, it's work in progress. It's a research project, basically. So we added a lot of allocator debugging. We basically went really aggressive with libBSD and RTEMS, kind of like cutting down code size. And also a thing we discovered that basically you have 1 allocator per thread, which kind of like grabs a lump of memory, basically. And for some reason, we couldn't get rid of the dirty scheduler. That's also a thing that we need to find out. Why can't we get rid of the dirty scheduler? So this is an optimization, because if every thread, like every scheduler thread has its own allocator, you have less locking. But you can actually do that away and pay for the locking. And then you have like less fragmentation and less big chunks of memory doing away. And that had quite some impact. We have lots more free memory. And the beam bin is now below 3 megabytes. That means it would fit into the internal RAM altogether, so even with contiguous loading, or into flash. So yeah, that sounds like a promising space. And actually, we actually loaded much more now. Oh no, I messed it up now. Sorry. So, yeah, no, it is actually demo time. So, that was correct. So, I have a GRiSP Nano here. I have a SD card in. And on the SD card, we currently have a thing where we load like quite a bunch of modules. And then, well, let me open the serial terminal. Oh yeah, it's open already, so let's make that big. So I hope that's readable. That's my last test run. So I plug in the micro USB here. So that's the console, basically. And we see it doesn't work. Fun. Okay, I decided to disconnect. So let's close the window. And let's open the port again. Oh, I know why it isn't connected. The other end needs to be plugged in too. These cables have two ends, you know. Hardware. And now it's actually showing up, and we open it, and now the font is small. I hate that. So, and let's push the reset button so you can actually watch the whole thing. Where is it? There. Okay. So that's Nano bootloader thing. Now it boots beam.bin. You see that here coming up. And there's a lot of stuff scrolling away because we have all this debug stuff, like we print what the allocators do. You see the fragmentation of the RTEMS allocator all the time. I think that was instrument, this large thing here. So we actually added a way to have the instrument module loaded very early so we can actually use the very nice code instrumentation that the OTP team brought in to actually look at things, but we are not using the data yet for that. And you see here's like kind of like a lot of like little things. We will talk about that later when we have time. So yeah, it's quite slow now because we have lots of extra code running. But it doesn't matter as long as it boots, because normally on the energy harvester we would boot once and then we would just sleep and wake up. You can see that the fragmentation is slowly getting higher, 33%, etc., etc. I didn't account for this running so long because I have another one. So I think we are almost there. Query list compiler, random, regular expression, sets, string. Oh, you see we are well into standard lib now. And then basically we didn't start our application, but we kind of like started our own process that we loaded, which currently it's counting, basically. Now, you see this is running on this, basically. So we run Erlang code. And we run Erlang code and print out text, etc. So maybe we have time for a little other one. I have another SD card. That's basically booting how far we can get. But I'm not sure. I think I need to continue with the slides while I'm doing that. So I swap the SD card. And that's kind of like we boot until we crash and run out of memory. That's our current state, how far we got. And I think I go back to my slides while I keep that running because that runs too long. And we have a look later, maybe, if there's time. Okay. So that was the partial demo. So yeah. So actually the result of the thing that I talked about before the demo, like doing all this aggressive allocate debugging, we load 45 modules more. We're getting there. So you see we get to query list compiler here. Maybe a short explanation on our kind of like debug thing. So that's the largest free block of the RTEMS memory related to total free. So that's the fragmentation that I already explained, and that's kind of like stuff that we print out, number of blocks allocated, allocated number, memory for this allocator, etc., etc. So all these values, I don't read them. And you see these lines, there's temp alloc, literal alloc, and LL_alloc is disabled still. And that is Erlang allocator. So basically the Erlang runtime has lots of allocators and very tight documentation. And it's, it's a challenge actually to get your mind wrapped around it. And the Beambook was actually, shout out to the Beambook. We looked into that thing too, and the documentation, we used everything. But it's still interesting. So time to enable this kind of like mythical LL allocator that we are still disabled. So that's our current flags for the allocators after a bit of tuning. And that actually, same kind of like size in the beginning, we can load 14 more modules. And now we got to our nemesis, which we already know, at least I knew. I think my team was a little bit optimistic about it. Unicode, it's 0.5 MB, one module. That's not going down well. And actually, what do you need Unicode on such a small module? So my team thought like, yeah, we delete it. But because I talked to the OTP team before, it's like, yeah, it's not so easy because it's used in a lot of places. And we probably need to stop it. So we will probably make some version of Unicode. And I think when we get over that, we will be booting to the shell very soon. So that would have been the kind of like the extreme goal for this talk, show you the shell. Well, we didn't quite get there. We got to Unicode, and probably by now we can actually switch window, maybe. No. I need to kind of like hurry on. Let's show you the graph first. So that's now we have more data now and more graphs. So we have, as you see, you can see the evolution basically how we build more and more tools while we are doing that. So so there's still this kind of like this the RTEMS memory kind of like using the LL allocator. So the LL allocator is the long-lived allocator. It is to be used for long-lived things. So not things that are kind of like allocated and freed all the time very quickly. And that's why it can actually pack the memory better. And basically it grabs big chunks of memory and fills them up basically. And that's why you see on the RTEMS side there's not much happening anymore. While basically here you see that that's inside the allocators. So the top one is the long-lived allocator, where the actual code goes now. The red one, the second line is the literal allocator, and this is the temp allocator for temporary things. So which kind of like allocates, frees. You see that it kind of like frees everything. So what do we do next? We build some kind of like version of Unicode Lite. So for example, something that assumes everything is a 7-bit ASCII. Because 7-bit ASCII is valid UTF-8 actually, and then kind of like stop everything until it works, and have a Unicode Lite module in there. Well, we need to use the internal RAM more because 3 MB is a lot if you have only 16. 16 to 19 is quite a big thing, or even the flash, because now this is kind of like shown on the horizon that we can actually fit it in flash, and also kind of like we need more information about like how to cut out things from kernel and standard lib. And of course, then once we boot to the end, basically we need to start working on this energy-aware booting, basically kind of like set up the thing, try to boot everything, or even in the boot script kind of like measure the energy again and say, hey, do we still have enough juice to load another one? No, okay, let's sleep a bit. And then you wake up a bit and load a bunch of modules more, so stuff like that. And once we have all that fixed and running, then we will run a Kickstarter again and we'll sell the board. Because currently there's 5 of this, or maybe 10. We made a few more.
It's again when I was loading more and more modules, especially that we were stuck for some time. I was hoping that I would be able to put the screenshot of the shell showing up, but that we didn't reach yet.
When I ran my first Erlang process without kernel, without application controller, with anything, because the boot loop execute commands from the script, and I basically had to remove everything. And at last, I just called a function in one of my modules that would call a spawn, and so my process was just the son of init.
That was the first.
So this is like a few like yesterday or something, like when I started figuring out, I started having a hint of how these things works. And because now what I'm doing actually has an effect, and now I can actually tweak things, and it makes sense. And before I was just like this and say, okay, this doesn't do anything. This doesn't work. This why?
Yeah.
So yeah, I'm kind of proud to kind of start to understand.
You figured it a lot out.
But yeah, but even but you see, like I kind of start to understand, and before it was black, and now it just whoa, this is complicated.
The usual thing. You learn more, and then you know what more you need to learn. So that's it. We are building an IoT platform, GRiSP.io. You can check it out as a beta. If you can't reach it, we are currently there's kind of like an extortion racket going on, which is called like virus and vulnerability scanning tools. There's 1 million of them. And if they pick you up for one time, it's very hard to get out. So it might not be reachable at the moment. We are working on it. Because they all say, yeah, pay us, and we tell you why it's not working. And then you get basically dozens of those. And also, a thing that we actually also already wanted to kind of like run after the Codebeam America, but we didn't get to it yet. We actually want to run a Kickstarter to work on Rebirth 3, to get some funding for Rebirth 3, to actually, with the goal of making it ready to be possibly included in OTP. So if you do it right, then the OTP team might be interested to have Reba in OTP and maybe even build OTP with it, which would then build faster. And that is my last slide. If you want to scan that, you can kind of like put your name in there, and then we tell you when it starts.
All right. Thanks, Per.
Not sure we have time for questions still.
Thanks for the noise. Do we have any questions in the room? Please wait for the microphone.
Was there any functionality in the Beam or the runtime system that you were missing that would have made this project easier?
Well, the thing is, it's clear that it was not optimized for tight memory, basically. That's not a thing that was a goal. It was optimized for speed and all kinds of things, which are important for other systems. So, but actually really missing, I wouldn't say so, because it was not too hard, basically, to get the instrument module into the preloaded thing. You get all the bits and pieces you need. It's all there. It's great, actually. There's a lot, but there's so many bits and pieces. It's actually the learning is more the learning path is more the thing. The things you learn while you make it work. By the way, that's the last demo. If I scroll up, you see we got to Unicode.